Hello, good morning.
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 How are you today? Noel and Kelvin.
Okay.
Morning. Yeah. Okay, so are you ready? Did you check your lecture notes already? We stopped somewhere in chapter 1 still, right?
Yeah.
Yeah.
Yeah. Okay, so today we're going to continue with the chapter 1. And also after that, we're going to do a discussion. There's a bit of questions at the end. Did you check your lecture note at the end? If you notice, there is one question. So we're going to discuss that together during this lecture at the end of this chapter 1. So, okay, without further ado, I will continue with the last section which we stop on. All right. Okay, so we stopped, I think, somewhere around stacks, did we? Stacks, always did. Um, we touch a little bit about stacks, and then we go after queue, right? Yeah, I think we stop at stacks, right? Correct or not? Yes.
Yeah.
Yeah, I think we stopped halfway through stacks. Yeah. Okay. Because after that there will be a queue, and then okay, list is not here. List is already done above, right? Yeah. Okay, so we start with stacks. Okay. Okay, as I mentioned previous lecture, stacks are like collections of objects which are stacked with each other, and then the objects are inserted and therefore removed according to that last in, first out lethal. Okay, principle. Therefore, it is linear. Linear means one after another. Entries in which it can only be removed again in the reverse order in which they are added. So the last entry added will be the first one to be removed. This one we watched before, right?
May I begin by saying that the stack is a remarkable,
This is just a recap.
absolutely remarkable data structure. One of my favorites, in fact. This is part 1 of 3 in the stack videos. Part 2 will consist of looking at a stack implementation, and part 3 will be some source code for how a stack is implemented using a linked list. So here are the topics that we'll be covering in this video as well as the others. First, we will answer the question about what is a stack and where is it used. Then we will see some really cool examples of how to solve problems using stacks. Afterwards, we will briefly look at how stacks are implemented internally and the time complexity associated with the stacks operation, and lastly, of course, some source code. Moving on to the discussion about stacks. So what is a stack? A stack is a one-ended linear data structure which models a real-world stack by having two primary operations, namely push and pop. Below you can see an image of a stack I have constructed. There is one data member getting popped off the top of the stack, and another data member getting added to the stack. Notice that there is a top pointer pointing to the block at the top of the stack. This is because elements in a stack always get removed and added to the top of the pile. This behavior is commonly known as LIFO, or last in, first out. Let's look at a more detailed example on how a stack works and how things are added and removed from a stack. So let's walk through an example. On the left side, I have some instructions on what we need to add and remove to the stack. So the first operation is a pop. So we remove the top element from the stack, which is apple. So boom, apple is gone. Now we push onion onto the stack. So we add onion to the top of the stack. Next instruction says to push celery onto the stack. Next is watermelon, which we put on top of the stack. Next operation says to pop, so we remove the element at the top of the stack. This is the watermelon we just added. The next operation, also a pop, so we remove from the top of the stack. This is celery. And the last operation, push lettuce onto the stack. So we add lettuce on the very top of the stack. So as you can see, everything operates on the top of the stack. We don't have access to anything else but the top of the stack. This is critical in our understanding of how a stack works. So when and where is a stack used? Stacks are surprisingly used absolutely everywhere. They're used in text editors to undo text you've written, in browsers to navigate backwards and forwards. They're used in compilers to make sure you have the correct number of matching braces and in the right order. Stacks are used to model real-world stacks such as books, plates, and even games like the Tower of Hanoi, which we'll get to shortly. Stacks are also used behind the scenes to support recursion by keeping track of previous function calls. When a function returns, it pops the current stack frame off the stack and rewinds to the next function that is on the stack. It's rather remarkable that we use stacks all the time in programming and never even notice it. Something else you can use stacks for is to perform a depth-first search on a graph. A depth-first search can be done manually by maintaining your own stack or by using recursion. Well, guess what? Both use stacks, as we have just discussed. Complexity analysis. So the following complexity table assumes that you implemented a stack using a linked list. Pushing takes constant time because we have a reference to the top of the stack at all times. Well, the same argument goes for popping and peeking. Searching, however, still takes linear time. The element we're searching for isn't necessarily at the top of the stack, so we may need to scan all the elements in the stack, hence requiring linear amount of work. Now, here's a cool example of a problem using stacks. Problem. So given a string made up of the following brackets, round brackets, square brackets, curly brackets, determine whether the brackets properly match. So analyze the examples below to understand what type of bracket sequence is valid and which ones are invalid. So before I show you the solution, try and come up with a solution yourself. Hint, use a stack. Okay. In this first example, consider the following bracket sequence. As we are processing the string from left to right, I will be displaying the current bracket and the associated reversed bracket. So let's begin. For every left bracket we encounter, we simply push those on the stack. So this is a left square bracket that I've highlighted in light blue. So we push this one on the stack. Same goes for the next left square bracket and this left curly bracket. Okay, this is a right square bracket. So we encountered a right square bracket. We need to do two checks. First, we check if the stack is empty. If so, the bracket sequence is invalid. But if there are still things in the stack, then we pop the top element and check if its value is equal to the reversed current bracket. Right now, the top element is equal to the reversed bracket, so we are good. Next is a right square bracket. So is the stack empty? The top stack equal to the reversed bracket? Yes, it is. So let's keep going. A round left bracket. Let's push it onto the stack. A right bracket. Is the stack empty? No? Okay, so we're good. Is the top element of the stack equal to the reversed bracket? Yes, okay, so we're good. Another right bracket. Is the stack empty? No, okay, good. And is the top element of the stack equal to the reverse bracket? Yes, okay, good. And now we're done processing the string. We need to make sure the stack is empty now. Why is that? Well, in case the last few characters in the bracket sequence were left brackets, they would still be in the stack, right? But our stack is empty, so we can conclude that this bracket sequence is indeed valid. All right, let's do another example with another bracket sequence. So try and work this one out. So the first bracket is a left bracket, so we push on to the stack. The second bracket is also a left bracket, so we push on to the stack. This next bracket is a right bracket, so let's check if the stack is empty. No, it's good. And is the top element of the stack equal to the reverse bracket? Yes, it is. This next bracket is a right bracket. Is the stack empty? No, so we're good. And is the reverse bracket equal to the bracket at the top of the stack? No, it isn't. So this bracket sequence is invalid. So here's the pseudocode of the algorithm we just ran through. So if we let S be a stack, then for every bracket in our bracket string, we can get the reversed bracket for that current bracket easily. So if our bracket is a left bracket, push it onto the stack. Otherwise, we check if the stack is empty and if the element at the top of the stack is not equal to the reversed. If either of those conditions are true, then we return false. Otherwise, we return whether the stack is empty or not. And if it is empty, then we have a valid bracket sequence. Otherwise, we do not. I want to take a moment and look at the Tower of Hanoi, a very popular game amongst mathematicians and computer scientists, to see how it relates with stacks. The game is played as follows. You start with a pile of disks on the first peg on the left, and the objective of the game is to move all the disks to the rightmost disk pile. At each move, you can move the top disk of any pile to any other pile with a restriction that no disk be placed on top of a smaller disk. So we can think of each peg as a stack because we're always moving the top element in a peg and placing it on another peg. So shall we play? I will let the animation run and you will see how each peg acts like a stack. It's pretty cool. So you just saw how transferring elements from one peg to another is exactly the same as popping a disk from one stack and pushing that same disk onto another stack, given that the disk you're placing on top is smaller. So that's really cool. All right, in the next video, we're going to quickly look at how a stack is actually implemented. If you're interested in some actual source code for a stack, that can be found at the link at the bottom of this slide. I will also be going over the source code for a stack in the last video of the stack series.
Okay, so that is stacks, a little bit of a stacks. So you know how it works. Now stacks basic operation would be these. Push E, pop is empty if the stack empty, peek, and clear. Okay, these are the basic operation of stack. Okay, like I said, stack is like a derived from a metaphor of a stack of plates in a spring-loaded cafeteria cafeteria plate dispenser like this. So that's how they get the idea of the name, the term stacking. Okay, so this is a stack implementation.
Welcome to part 2 of 3 in the stack series. This is going to be a short video on one way to implement a stack. So stacks are often implemented as either arrays, singly linked lists, or even sometimes doubly linked lists. Here I will cover how to push nodes onto a stack with a singly linked list. Later on, we will look at the source code, which is actually written using a doubly linked list. Okay, to begin with, we need somewhere to start to be in our linked list. So we're going to point the head to a null node. This means that the stack is initially empty. Then the trick to creating a stack using a singly linked list is to insert the new elements before the head and not at the tail of the list. This way, we have pointers pointing in the correct direction when we need to pop elements off of the stack. As we will soon see, the next element, however, we need to push onto the stack is a 2, so let's do that. So we create a new node, adjust the head pointer to be the newest node, and then hook on the node's next pointer to where the head was before. And we use the same idea for 5 and also 13. Now let's have a look at popping elements. This isn't too hard either. Just move the head pointer to the next node and deallocate the last node. So here we pop the first node off the stack and set the node's reference to be null, so that it will be picked up by the garbage collector if you're coding in Java, and it will since there are no other references pointing to it. If you're in another programming language that requires you to explicitly deallocate and free memory yourself, like C or C++, now is the time to do that, or you will get memory leaks. Getting a memory leak in a data structure is one of the worst kinds of memory leaks, especially if it's a custom data structure that you intend on reusing. So keep watching out for that, not only in this video, but in all the data structures that we will be covering. If you see in an implementation that I'm not correctly cleaning up my memory, please point it out to me, or
So that is the implementation of stacks briefly. Now this is application of stacks in the real life every day. Okay, if you see in their icons in your application, you sometimes see this undo. That is a function of popping. And another one is that you see this word structure. Whenever a machine actually execute reading, they will usually go last in, first out. Okay, read from here. First in, last out from here. So that is basically a stack application. And also here, this is last in, first out. A person just put down all the information, and then the last in would be the first one to be um, put on top and read. Okay, so this one is any application that requires LeFo processing, checking for palindromes. Palindrome is referring to a same word that can be read exactly the same way, or forward and backward. So, like for example, these words noon, it can be read backward. So stack basically um, checking for this, and then they are reversing a string, etc. for the application. Okay, look, if you notice the words NOON, it reads the same way backwards and front and back the same. NON, NON, KAYAK, KAYK. The same goes with race car. Okay. So this one, a Java collection of framework from the Java utility stack class. The terms that you can use from the Java utility stack are these. Each has its own meaning when you call upon writing this up inside your functions your program. For example, this plus stack indicates create an empty stack. Plus empty boolean returns true if this stack is empty. Okay, and peek e returns the element into this stack, and pop returns and removes the top element in this stack as well. Push is obviously to just remove that from the stack, and then the search is to return the position of the first specified element of the stack. Oh, so this is a reversing a string. For example, you have this IBMRD stack basically checking for reverse string. This is a push operation. First, it enters into push I, and then after that, push B, M, R, and D until everything is pushed in. After that, popping by LeFo, last in, first out. First goes from D, then goes from R, and then M is popped out, and next B, and then last but not least is I. So this is how it works, yeah, for stack, because it works back last in, first out. This is just an illustration of that. So this is a reversing. This is a instruction or stage where you actually understand about how that works of a stack. First thing is that you need to have an empty stack. Push every character that was inside that string which you have into the stack, and then so if the stack is not empty, you keep pushing in. Otherwise, you pop a character from the stack based on the specification which you saw in the video, and then you display the character, the next one to be pushed in, and then you popped it out based on the comparison after that. So this is a reversing a string sample code. I did not have it here. Maybe I can give it during our practical time, so you can see how stack is used in source code in your Java. So this one is called mod method reverse in string toolkit.java. So this one is already illustrated inside the video from the video. This is about matching brackets. Yeah, how you put in these inputs brackets, blue, red, green, and blue into the empty stacks, and how we pop it out based on the comparison. Okay, so that is how already been illustrated in the video. So this is checking for balance on using these elements. Okay, the brackets. So again, this is to explain to you in point-based that you have to use a stack to store the left brackets. Brackets include parentheses, square brackets, and braces. So how you compare them it's already done here. Okay, so then after that, what do you do next is you traverse expression to process each character by referring to this. Yeah, like how you saw in the video, compare between the brackets if whether or not it is same position or in the reverse position, so therefore which to pop, and then that what is next. Okay, so so this one is the checking for balance of the same. This one illustration, right? First you push in the curly bracket, and then after they push in the same square bracket, then you push in your normal bracket. After that, you start popping one by one, comparing whether or not it is valid. Okay, so the content of stack during the scan of expression that contains the balance delimiters, which are referring to the brackets. Okay, so then you compare one after another based on what the video has explained. Every time there is a non-similar sides of the pair, you should pop it out from the stack and then continue with the next one. Okay, so see, this is the contents of the stack during scan expression until you reach to the last delimiters, and then yeah, is it not same? So whatever it is not the same, you pop it out. Okay, until the stack is empty and curly bracket is encountered. Okay, so this one, checking for balance algorithm, is on algorithm 1.1 check balance. Let's see that. I have it with me. I'll show you how it looks like. Okay, so this is how your source code look like when you're trying to compare the check balance of the curly brackets, the brackets. Okay, return true if the parentheses, brackets, and braces in the expression are paired correctly. So look at the code, is balance. If is balance is true, if the comparison, the brackets are similar, therefore, and it's not the end of the expression, you do this, switch characters. Okay, and then keep doing it, push the next character onto the stack and break, stop, and then check again whether it's similar. After that, you put it in, and then you check whether the stack is empty or is it the same. So if not the same, then false, and therefore what do? You pop it out from the stack, and then you end, and if again you check if the stack is empty. If it is empty, then you end, otherwise you continue with whatever is happening here, you compare, and then you pop it out. So return is balance. Okay, so that is your example of check balance to check proper pairing of all the delimiters. We are referring to parentheses, brackets, and braces. Next one, we are looking at infix, prefix, and postfix expression. Okay, so what are these? These are basically on how the computer reads in stacks all the operation which is happening. Okay, so this infix is none other than binary operators which appear between the operands. Okay, for example, here a plus b, operands is plus, operators is plus, and then operands is a and b. Prefix operation expression would be the operators appear before the operands. So in this case, example is your plus appears before this operator, you call it plus, okay, appear before the operands A and B. What about postfix? Postfix expression is binary operators appear after operands. In this case, your operand will be sitting at the back. Okay. First thing, infix in between. Second, prefix would be in the front, which is before your operand. And then postfix will be at the end. Your operators will sit at the back of your operands. So this you don't need parentheses or precedents because you already have that specific infix, prefix, and postfix expression. Okay, this is an example of how you execute infix, prefix, and postfix. There is, if you notice, exercises at the end, which is referring to this one. You are supposed to transform each of the following infix expression to its postfix and prefix form. Now look at the example here. It's quite similar to what we have here, just an illustration. A plus B multiplied by C plus D. What is your prefix? That would be your operands. Your operators appear before your, this prefix, right? Prefix, your operators appear before your operands. Therefore, here your plus would be in front. You have two pluses. And then you have A multiplied by B, C, and D. Okay, so there's prefix. Prefix, your operators appear before your operands. Yeah. Okay. And then postfix expression would be, what is a postfix? Postfix is your operators appear after your operands. Your plus would be at the back. Okay, anything that is plus minus at the back. Yeah. So that would be A, B, C, and then your operands. Your operator will be at the back, plus, multiply, plus, D, plus. Okay, so this is how it is to be read in your system. And infix, the next one example is A plus B in the bracket multiplied by C plus D. So prefix operand always at the back, and then your operator would be in the front. Yeah, operator appear before the operands. So multiply plus AB plus C and D. AB plus CD. This will be in the front of that AB plus CD too. Yeah. Okay. And then postfix, that will be way at the back. That means you see that it doesn't move, it doesn't really change, except that the front part of this is moved to the back. And this one, A multiplied by B plus C multiplied by D, but B, your plus sign and your multiplication but sits in front, and then your A, B multiply CD, A, B, C, D. That and that goes here. This in front. Okay. Postfix, AB multiply CD. Same goes with this one. You just transfer it to the back. Okay, next expression, last but not least, A plus B plus C plus D. This is quite simple for prefix because all operands would be at the back and operators would be in the front. Whereas postfix expression, you have AB plus C plus D, and basically it operates way from behind. So your operator will sit at the back. It's quite tricky, but you have to look into how it operates. Yeah, so that is your infix, prefix, and postfix. And then you can try it on with this one. Yeah, you can try on with that one. So A plus B multiplied by C, A multiplied by B slash divided by C minus D, A divided by B plus C minus D. Okay, try, maybe you can try on this one, yeah? So that is the answer. Okay, you got it? You got it, guys? This one now you should do your infix answers here already, right? One example. Okay, so almost the same, just that this one would be postfix, the one which I showed you earlier. This is at here, this is in here, but the other one is that this is here and this is here. That's why it's just the same actually. See? Yeah. Okay. So that is your exercise. Are we okay? No, Kelvin?
Okay.
But it's quite confusing, but you have to
The
just
postfix and prefix, the order reversed only.
yeah, it's reverse because as you see here, yeah. Based on this infix, always your operator is in between the operands A and B. If operands mean it doesn't matter what alphabet you have, C, D, okay, A, B, C, D, you know, all those are operands. It always sits in the middle. So that's not really tough. Yeah, so but this one is always given to you first. And then what about your prefix? I'm not sure if it is an examination. Sometimes probably they give you prefix and you were to give what is the infix and postfix. But usually maybe they give you infix and then what is the prefix expression and the postfix expression, just like how the exercise is. So quite tricky also, but you have to just look at the example and try to do it based on this rules, postfix expression. So prefix always operands sits at the back, operators sits in the front. Yeah.
Oh, okay.
Always sits in the front. The operators, your AB will be at the back. Here, always in the middle. This one, it's way back. Okay, this is just a reverse of your prefix. Postfix is after. Prefix is before. Okay, infix is between. So I got this example. Read as much example as possible. Okay, and this one is already given to you as well. You're supposed to do this, but never mind, I'll show you. Okay, so this is postfix. If you notice my diagram a while ago, which I shared to you, my prefix, I put it over here. My postfix is over there. It doesn't matter the sequence, but the thing is, you only need to know what is postfix, what is prefix, yeah? So over here, obviously, postfix basically refer to your operator sits at the back. So you know post means at the back, pre means in the front. So what is the answer for that? Okay, right there. Okay, so AB multiplied by C, everything will go at the back. Okay, tricky part about this is that you have to understand which goes where for postfix, but because the rule says that all the operators sits at the back. So here, A multiplied by B divided by C minus D. So here, your A and B combine, and then it multiply by your C and D, and then it push out the division, which is minus, and your division over it to the end. Okay. And then this one, A divided by B plus C minus D is it brings out your operands to the front and then divide, which means all these are combined, and then divide, and then the plus and the minus are pushed to the end, to the end. And this one same goes with that one. Always they combine your A and your B together instead of putting this in the middle. And then you put that in between here, and then your plus goes there, and then your minus goes there. Push. It's just pushing to the back. Okay, what about prefix? Prefix is, again, prefix is pushing it to the front. Hang on, what is the prefix? Prefix is to the front, yes. Okay. To the front, yeah. So basically, your operand should sit same way like how you arrange here. You can arrange the same way here. Here it says plus, go to the front, and A multiply by B and C. Okay. Next one is your division sign, multiplication sign, push to the front, your AB minus CD. Okay, you have to refer to this one. Okay, this one and this one put in the front. AB minus CD. Next, what is prefix? Prefix operator sits in the front. This case, your plus and your division, which is here, plus and division. So you combine AB minus CD. Okay, AB minus CD. This sits in the front. This sits in the front. Okay, and AB combine, and then you minus with the CD combined. Okay, so that is prefix. And last but not least, your prefix for D, you push minus and your plus to the front together with your division. Okay, and then you put everything to the back. Okay, so it's kind of tricky sometimes, but you just have to look into how you arrange your postfix. Okay, I think it's based on your postfix, and then you arrange your prefix based on that. Everything goes to the front. Yeah, minus, plus, division, A, B, C, D. Is that okay? Quite tricky, right? Yeah. Okay, so that is infix, postfix, and prefix. All right, so problem evaluating postfix expression. These are the calculation. Basically, this is how it looks like when it does this one. First thing is that 5 plus 3 divided by, multiply by 7 minus, okay? And then what it does first is that first 4 and 5 is added, and then you plus with 3 and you multiply with 7 and then minus. But over here you have done with this one. You multiply 9 with 3, 9 with 3 multiplied, and then it becomes 27. Then you bring down this, and then this minus this equals 20. Okay, so that's how it operates inside the system, basically. Okay, so this is a postfix expression, why you get all this. Okay, so if you do it normally, how we do normal manual human calculation, we just say 45 plus 3 divided by 7, and then or minus 7 after that. But this machine is just reading it this way, plus this one first, and then you put it down after this is done, and then you put it down. This will be multiplied after multiplication, and then this one is settled, and then you pull it down. Okay, push it in, and then that is executed with the operators here based on that. So therefore you get 20, right? Okay. So evaluating postfix expression by using a stack of operands. Basically, explanation is to traverse the expression to process each character. in a stack, if it is an operand, you push it into the stack. If it is an operator, you pop the two elements from the stack. So here it says that the first pop execution returns the right operand, while the second pop returns the left operand. And then what do? You perform the operation on the two elements and push the result of the operand into the stack. Let me see, what is that? Okay, I don't have that. I thought I have the source code. I don't have that. Okay, so this is the explanation for this one. Yeah, traverse the expression into process each character. To process each character, if the operand, push it to the stack. Okay, if it is an operand, what is operand? A, B, C, D, push it into the stack. Okay, okay. So your operand basically is allocated value of A is 2, B is 4. So if it is A, you push in 2. If it is 4, you push in 4. If it is B, you push it in 4. And then after that, you have the operator. Okay, so the stack during postfix expression, this particular expression AB, and then divided by AB division, and is basically is expressed like this. Okay, first push in 2, next push in B, which is valued at 4, and then you put in your operator, which is this division, and then you recheck. Okay, after that, slowly you pop out, which is last in. Then first thing here, it says you pop out your operator. Next, you pop out the next one, operand 4, which is referring to B. Next one, you pop out that you are left with number 2. So after that, you pop that out as well. Okay, and then after that, you push in 2 divided by 4 into the stack, which is 0, which returns you 0. Okay, so that is how actually your postfix and prefix and infix is executed. You cannot see that because that is executed in your code, in your system, if you were to execute a stack. Okay, that is basically just the logic on how it operates. So a while ago was a postfix. This one, evaluating postfix expression. Okay, under this expression, AB plus C and division. When A is 2, same concept, B is 4, and C is 3. How it goes, I pop in both operators, and then you put in 4, and then after that, you have your operators goes in. Okay, so this is how it returns the answer to your table. This is how it gets into your table with the illustration of this. Okay. 6, 2 plus 4, you have 6. And then you put 3 in there, which is C, and you divide it with this operator, and then you pop out that operator, you become, you divide it with the operator, that becomes 3. Okay, 3 divided by 6, you return the answer of 2. So that is your evaluating postfix expression rules and how it computes and give you the answer of what you have assigned based on operands and operators, which is each allocated with the value of 2, 4, and 3. Okay. So there's an area of memory in your computer known as the system or program stack, which is used to allocate memory for method calls. Okay, so an activation record is, what is it? A portion of memory on the program stack to function the same to call a method, and then it's store the called method arguments into local variables and reference with the current instruction program counter. So this is just calling the function, right? Calling the method on how to actually execute your what you call your functions in your program. Function call, your method call. You have a, I think you guys have done that in your coding, right? How did you? If you notice inside your code, you have calling of functions, calling of methods, and how to basically repeat the same operation in one particular section of your code, that it's basically save time for the programmer to actually keep doing the same thing, redundancy of typing the same particular method or function on how to basically execute the same operation in different modules. Yeah?
Oh, yeah.
Yeah, so that's how you call your method calls. So if you can visualize what I'm saying, so basically this is stack has that kind of function. Okay. So what happened when a method is called? Runtime environment creates activation record, shows method state during execution. And so activation record push onto the program stack, and then that happens by executing the method. And then next method down is the one that called current method. So like I said, this one is basically calling the method and how it can execute the same in every other program which perform the same function. So it saves time and you don't have to rewrite the same code, but you just call the method on how that particular action can manipulate whatever your set variables inside your program. Okay, so that is your method. So this is example. Program stack at 3 points in time, which is referring to A, when main begins execution, B, method A begins execution. When method B begins execution, it's C. Okay, so main program and then stack, and then after that you have method A, and then you have method B, and then you go for calling of functions again, method C. So you execute method C, method B. So basically you have A and B interchangeably in your stack. Okay, so public static void main, you define your variables. Okay, integer x equals to 5, integer y, which is referring to method A, okay, of x variable. So you and main, and then you have public static, another what do you call that, module here that basically define your integer method A as integer A. Okay, basically you're calling this already constructed program, which is identifying method A as x. Okay, x is equivalent to 5 into this other program here. And then after that, you run a method B. What is method B? Method B is basically you want to set method B. Yeah, this one, your integer changed to no longer 5, but you change to 2. So basically you call upon the same method, but you change the variable twice. So first, second, okay? And then this one, you also change it into from A to B. Okay, so this is just calling of a method to be executed in the same program, but doing and executing the same function with change variable given. Next one is queue. Any questions so far? This one you need to understand. Probably if you have the code, you can know. I believe you guys have already done. Yeah, I've collected your script. Kelvin, please submit it into the box. Yeah, again, sorry. You have to submit that into the box. I need to keep it into my drive. Right, Kelvin? So Noel has already posted in the submission box. You gave me email. So Noel as well give me email, but he already submitted to the box. So I need that to be submitted in the box. So I don't have to scroll down into my email and then retrieve it and put somewhere else. So easier to put it in there so it goes into my drive straight away. Okay. All right. Next, queues. What are queues? Normal word queues mean just line up, right? Lining up. So it's a definition, a collection of objects that are inserted and removed according to the FIFO, first in, first out. Okay, stack is LIFO, please remember that. So queue is first in, first out. You queue first, you get it done. You queue first to buy a ticket, you get your ticket first. So that is as easy as that principle. So element that has been in the queue the longest will be the next one to be removed. Okay. Okay. Elements enter a queue at the rear of the back. Elements are removed from the front. Okay, so this is a linear collection of entries where entry is going to be removed in order in which they are ended. That means it doesn't go to the back, it goes to the front. Yeah, so there is no provision to search for an entry in the queue because this is just simple, this sequential, okay, in linear arrangement. Okay, this is queue example.
Let's talk about queues, probably one of the most useful data structures in computer science. So this is going to be part 1 of 3 in the queue series. So the outline of things we'll be looking at. Well, first, we're going to begin by talking about queues and what they are. Then we're going to go into some complexity analysis concerning queues. Then we'll discuss the implementation details of enqueuing and dequeuing elements from a queue, followed by some source code at the very end in the last video. So a discussion about queues. So what exactly is a queue? So below you can see an image of a queue, but a queue is just a linear data structure that models a real-world queue, having 2 primary operations we can do, which are enqueuing and dequeuing. So every queue has a front and a back end. We insert elements through the back and remove through the front. Adding elements to the back of the queue is called enqueuing, and removing elements from the front of the queue is called dequeuing. However, there's a bit of terminology surrounding queues because there's not really any consistency. When we refer to enqueuing and dequeuing, many people will use multiple different terms. So enqueuing is also called adding, but also offering. A similar type of thing happens when we're talking about dequeuing. So this is when we remove things from the front of the queue. This is also called polling elements. However, some people will also refer to this as removing an element from the queue. But the problem with saying that is that can cause some ambiguity. Did they mean removing from the front of the queue specifically or from the entire queue? Make note that if I say removing, I'm going to be referring to removing from the front of the queue unless I say otherwise. So let's look at an example of how queue works in some detail. However, first notice that I have labeled the queue's front and back ends so you know where I'm going to be enqueuing and dequeuing from respectively to avoid confusion. First instruction says to enqueue 12, so we add 12 to the end of the queue. Then dequeue, so we remove the first element from the front of the queue, which is 55. Another dequeue operation This time we remove -1 from the front of the queue. So next, enqueue 7, so add 7 to the back of the queue. Dequeue, so remove the front element being 33. And lastly, enqueue -6, so add it to the back of the queue, just like that. So now that we know what a queue is, where does this data structure actually get used? Well, a classic example of where a queue gets used is to model a real-world queue where you're waiting in a line at a movie theater or in a line at a restaurant. For instance, have you ever been to, say, McDonald's, where all the caches are full, and as soon as one of them gets free, the next person in line gets to order food? Well, that's a queue. So queues can also be really useful if you have a sequence of elements coming in, but you only need to keep track of, say, the X most recent elements. Well, you can add those elements to your queue, and once your queue gets larger than X elements, just dequeue, essentially. Queues are also often used in server management. So suppose for a moment that you have a web server that's idly waiting for requests from people to use your website, that at any given moment you can simultaneously serve up to 5 people, but no more. If 12 requests come in a short amount of time, you're not going to be able to process all of them as new ones come in. So what you do is you process the 5 that you're able to, and the remaining 7 get to chill in a queue waiting to be served. And whenever you finish processing a request, you dequeue in the next request, and then you start processing it, and you do this until the queue is empty. While you're doing this, if more requests come in to access your web page, well, you just add them to the end of the queue. Queues are also used in graph theory to perform a breadth first search traversal on a graph, which is actually really useful. We're going to see this example in the next video. All right, now concerning complexity analysis of a queue. So as we've seen, it's pretty obvious that enqueuing and dequeuing operations are constant time. There's also another operation on a queue I have not mentioned yet, and this is peaking. Peaking means that we're looking at the value at the front of the queue without removing it. This is also constant time. However, checking if an element is contained within the queue is linear time, since we would potentially need to scan through all of the elements. There's also element removal, in the not in the sense of dequeuing or polling, but in actually removing an element from the queue internally. This also requires linear time, since we would have to scan through all elements in the worst case. Okay, in the next video, we're going to look at some implementation details concerning a queue, so how it's actually done. So guys,
Okay, that's briefly about queue. I hope you know what is enqueue, what is dequeue. Enqueue is basically from the back, queuing from the back. You will being added entry from the back of the queue. Dequeue is just removing entry from the front of the queue. Okay, so is empty is referring to whether or not queue is empty. Get front is to retrieve, not to remove the front object of the queue. Okay, retrieve means you just get it and you want to process something with it. So size, return the number of entries in the queue. So this is the basic operation of queue. Okay, from your Java utility for queue interface, you have all these modifiers and type and method and description of each. If Boolean, you know, that is present true or false element, true or false description. So here you put add E element, insert the specified element to this queue if it is possible to do so immediately without violating capacity restriction. return true upon success, and throwing an illegal state exception if no space is currently available. This is to check whether if this is true, if it is empty, then what do you do? If it is not empty, then what do you do? Okay. So E is element, basically function to retrieve. Like I said just now, it is just purely retrieving, manipulate it, or do some execution with it, but not to remove the head of this queue from the front. Boolean is offering, Boolean is referring to, again, offer E, inserts a specified element into this queue if it is possible, checking whether it is valid without violating what is the restriction capacity. Okay, so if I can insert this, if it is empty, then therefore insert, otherwise, what do you call that? Abort. Yeah, abort the execution and proceed with the next execution. Next, E peak. A while ago, he mentions it's just retrieving. Also, do not remove the head of the queue. Return null if this queue is empty. Okay, and pull retrieves and remove the head of this queue, or to return the current queue to empty if it is empty. Okay, and next, last but not least, is to remove, retrieve and remove the head of this queue. So these are your Java utility queue interface modifier type, which you can use. All right. Java.utility concurrent.array blocking queue is a concrete class that implements. This is actually example or code. I will have to check this in my drive whether I have that. If I have it, I'll show it to you during class later on. When we are doing, I think I will share with you also code that you need to implement for your next questions inside your practical class later. So one of it is queue and array, queue and stacks. Yeah. So for now, this one I do not have it here. I will post it later if I have during practical. Application of queue. We already discussed or mentioned several times. In the real world, what you do is, this is your application handling calls, for example, to reservation center of a reservation, a restaurant. And then print queues. Print queues is none other than you send, there are several computers inside a local area network in one particular lab. Yeah, so then it is basically, if there are 2-3 computers trying to print all at the same time, and all the requests from the printer will be queued. Okay, so print queues. Round robin schedulers basically is to one of the program which is used to allocate a slice of CPU time to various applications running concurrently on a computer. Okay, what is this? This is basically scheduler. Each computer is allocated time that was allocated in here.
So
Let's
far, we
look
have
at this video.
discussed about 3 scheduling algorithms, namely the first come, first served scheduling, the shortest job first, and the priority scheduling. So in this lecture, we are going to discuss about the next scheduling algorithm, which is also a very important scheduling algorithm, and that is the round robin scheduling. So we will see what is this round robin scheduling and how it works. The round robin scheduling algorithm is designed especially for time sharing systems. So why is it designed for time sharing systems? We will understand that as we move ahead. And it is similar to the FCFS scheduling, but preemption is added to switch between processes. So this round robin scheduling algorithm in one way is similar to the first come first serve scheduling, but preemption is added to switch between the processes. And we will be seeing how it is done as we move ahead. So here, a small unit of time called a time quantum or a time slice is defined, which is generally from 10 to 100 milliseconds. So in this round robin scheduling, what happens is that we define a small unit of time which is usually called the time quantum or a time slice. And this time quantum or time slice is generally defined from 10 to 100 milliseconds. So it will fall between 10 and 100 milliseconds. And what happens is that each processes will be assigned this time quantum for its execution. So whether the CPU burst of the process is greater than the time quantum or not does not matter, but this specific time quantum is assigned to each process. And a process will be allowed to execute only for that particular time quantum in the first round. And after that, the CPU will be given to the next process that is waiting in the queue, and that process also will be allowed to execute for that specific time quantum, and then the CPU will be given to the next process and so on. So what happens is the ready queue is treated as a circular queue, and the CPU scheduler goes around the ready queue, allocating the CPU to each process for a time interval of up to one time quantum. So that is what I just explained. So here what will happen is the ready queue where the processes are waiting is treated as a circular queue. So I have shown this using this diagram over here. So think of this as a circular queue. So this is the ready queue, and the processes are waiting in this circular queue, waiting for its turn to get the CPU for its execution. So here we are having 10 processes P1, P2, P3 up to P10. So they are waiting in this queue, and when a new process comes, they will be added to the end of the queue or at the tail of the queue. So this is process P10, which is the last process. So if a new process arrives, it will be added after this P10 at the tail of the queue. So you may not be able to visualize the tail of the queue because it is circular over here, but actually it is not circular in shape. But just to make you understand, I have taken this diagram. It is actually just a normal queue where the CPU scheduler will move from one end of the queue to the other end and then come back to the start and again move from the start to the end, and it goes on like that. So that is why we have depicted it using a circular queue. So we have processes P1 to P10 waiting in this circular ready queue, waiting for getting the CPU for their execution. So what happens is there is a CPU scheduler that will assign the CPU to this particular processes. So first of all, the CPU scheduler will come and assign the CPU to the first process that is there, that is P1. So in this way, it is going to start like a FCFS scheduling, first come, first serve. So whoever is first will be first given the CPU. And for how long will it be given the CPU? It will be given the CPU for a particular time quantum. So there will be a particular quantum of time that will be defined, and only for that amount or that period of time, the CPU will be assigned to a particular process. So let's say that the time quantum is 5 milliseconds. So what will happen is the CPU will be given to P1 for 5 milliseconds. So P1 gets the CPU and uses it for 5 milliseconds. That is one time quantum. So after that, the CPU scheduler will come and give the CPU to P2, which is the next process that is waiting in this regular queue. So P2 will get the CPU and will also be allowed to execute for 5 milliseconds, which is that particular quantum of time. And after that, P3 will be given the CPU and will be allowed to execute for 5 milliseconds and so on. So it will go around like this in this regular queue. And when it reaches the end of the queue, what happens is that it will again come and check if P1 has completed its execution or not. So if P1 has completed its execution, then P1 does not have to get the CPU again. But if P1 did not complete its execution in the first quantum of time that it has received, then the CPU will again be given to P1 and it will again be allowed to execute for one quantum of time, which is 5 milliseconds in this example that we are talking about. And then it will go on like that for the other processes as well. So that is what happens in a round robin scheduling. Now we will see how this round robin scheduling is implemented. So if you understood the above example that I have taken, it is very easy to understand the implementation of round robin scheduling. So let's see how it is implemented. So what happens is we keep the ready queue as a first in first out queue of processes. So we are keeping the ready queue as a FIFO queue as shown here. So I've shown you a circular queue in the previous diagram. So actually what it is just a first in first out queue. So where we have a head of the queue and we have the tail of the queue. And new processes are added to the tail of the ready queue. So whenever a new process arrives, the process will be added to the tail of the queue. Then what happens is the CPU scheduler picks the first process from the ready queue sets a timer to interrupt after one time quantum and dispatches the process. So after this, what happens is the CPU scheduler will pick the first process that is at the head of the queue, and it will set a timer to interrupt after one time quantum. So as I already explained, the time quantum is a particular period of time that will be defined. So for different cases, we may have different quantum of times. So sometimes it may be 3 milliseconds or 4 milliseconds or 50 milliseconds and so on. So we will define a time quantum, and then once the CPU scheduler assigns the CPU to the first process that is there at the head of the queue, at that moment a timer will be set and a timer will be running, and then the timer will run for that one time quantum. So let's say if it was 5 milliseconds, it will be running for 5 milliseconds. So at the 5th millisecond, the timer goes off, and at that time, the CPU scheduler will take control of the CPU away from this process that was using the CPU, and it will give it to the next process that was waiting in the ready queue. And it goes on like that. Even this process will use it for that particular time quantum, then it will be given to the next process and so on. So once it reaches the tail of the queue, what will happen is the CPU scheduler will again come back to the first process and see if it has completed its execution or not. And if it has not completed its execution, it will give the control of the CPU to this first process again, and can again execute for one time quantum, and then it will go on like that. So we see that it is going in a circular fashion. So that is why I have shown you a circular queue in the previous diagram. Alright, so this is what happens. Now, when the CPU scheduler picks the first process from the ready queue, sets a timer to interrupt after one time quantum, and dispatches the process. So after this, what will happen? So there are two cases that can occur after this. So let us see what are those two cases. So here are the two things that can happen. So the first case is when the process gets the CPU, the process may have a CPU burst of less than one time quantum. So it means here is that we are having a time quantum, which is a particular period of time, as I already told you, and the CPU burst of the process may be less than the time quantum. So let's say that the time quantum that we have defined is 5 milliseconds, but the burst time is only 3 milliseconds. So then what happens? The process itself will release the CPU voluntarily, because the process itself is having only 3 milliseconds of burst time, but the time quantum that is assigned to it is 5 milliseconds. So it does not have to use the CPU for 5 milliseconds. So after using it for 3 milliseconds, that process can release the CPU, and it will do so voluntarily. So that is what we are talking about here. So when the CPU is released voluntarily by that process, what will happen? The CPU scheduler will then proceed to the next process in the ready queue. So when the CPU is released by that process that was using the CPU scheduler will then give the CPU to the next process waiting in the ready queue. So this is one thing that can happen. This is the case when the CPU burst of the process is less than one time quantum. So that is what happens. Now what is the next case that we have? So the next case that we have is the CPU burst of the currently running process is longer than one time quantum. So if the CPU burst of the process is longer than one time quantum, then what happens? So for example, if the time quantum that we have defined is 5 milliseconds, but let's say that the burst time of the process is 10 milliseconds, then what will happen? At the 5th millisecond, the timer will go off and will cause an interrupt to the operating system. So when one time quantum period has completed, the timer will go off and it will cause an interrupt to the operating system. Then what happens after that? A context switch will be executed and the process will be put at the tail of the ready queue. So that is what actually happens. So let's say that this is the process that we are talking about. It was at the head of the queue and it got the CPU for its execution and it was executing. Now the burst time of this process is actually greater than the time quantum that we have. So we are assuming that it is having a time quantum of 10 milliseconds. So if the time quantum is only 5 milliseconds, so it will execute for the first 5 milliseconds, and after that the timer goes off. Then what happens? It did not actually complete its execution. There are more 5 milliseconds remaining. So what will happen? This process will be taken from here and it will be put at the tail of the ready queue. It comes from here to here. It will come at the tail of the ready queue. So that is what will happen. And then the CPU scheduler will then select the next process in the ready queue. So what will become the next process? This will be the next process now because this has gone to the tail. So this is the next process, and this will begin its execution. So remember that when a process has not completed its execution and when the CPU is taken away from it, there is a context switch happening, and at that time the current context of that process has to be saved, because we know that this process did not complete its execution. So we have to save the current state of that process, because when the CPU will be given to the process again later on, we should know from where it has to continue its execution. So the context or the state of that process has to be saved. So that is also done in this case. So this is what will happen in the case where the burst time of the currently running process is longer than the time quantum. So if you see clearly here from what I have explained, we can understand that it is not actually the CPU scheduler that is going round and round making a circle, but the CPU scheduler is here always picking the process at the head of the queue. So what happens is, when a process did not complete its execution but has exceeded one time quantum, it is taken from the head of the queue and put at the tail. Then it continues in the straight way again. So the CPU scheduler will always pick what is at the head of the queue. So when this is put from the head to the tail, this becomes a new head, and the CPU scheduler will pick that process. So that is how it actually works. So this is a very important scheduling algorithm, and it is mostly used for time sharing systems. So as we see, the time is shared between the processes that we are having. So here we have to be also very careful about choosing the time quantum. If we are choosing a very big time quantum, there may be some disadvantages. And if we are choosing a very small time quantum, there will be too many context switches that will happen. So we have to strike a balance between these two to make this algorithm work in an efficient way. So if we are choosing a very large time quantum, then this round robin scheduling algorithm will become like a first come first serve scheduling algorithm. Like for example, let's say that we have a time quantum of 50 milliseconds, and then the process that is at the head of the queue is having a burst time of 40 milliseconds. And then the other processes that are waiting in queue are having smaller burst times of, let's say, 3, 4, 5 milliseconds and so on. So what will happen? The scheduler will pick the first process that is at the head of the queue, and it will be assigned the CPU, and the time quantum that we have assumed here is 50 milliseconds, and the burst time of this process that we have assumed is 40 milliseconds. So this process will be executing for that 40 milliseconds completely, because the time quantum is anyway larger than that. So for that 40 milliseconds, these processes will be keep on waiting for this process to release the CPU. So it is becoming like a first come first serve scheduling. And again, these processes are starving for a long time for the CPU. So if we are having a large time quantum, that is what will happen. And also if we are having a very small time quantum, what will happen? There will be too many context switches. That is, let's say that the time quantum is only 1 millisecond. And if this process is having a burst time of 5 milliseconds, we see that it will first get the CPU and it will be executed only for 1 millisecond. Then it will be switched. Then the next one will get, and so on. So we see that this process that is having 5 milliseconds of burst time has to be switched a minimum of 4 times. So there are so many number of context switches happening. So that is also not a very good thing for an efficient algorithm. So we have to strike a balance between the two. So that is how the round robin scheduling algorithm is implemented, and that is how it works. So in the next lecture, we'll be discussing about how to calculate the average waiting times and the average turnaround times for a round robin scheduling. And we'll also see the factors on which these things depend. So it is a bit different from the other scheduling algorithms that we have discussed so far. So we will be taking it up as a different lecture. So I hope this was clear to you. Thank you for watching, and see you in the next one.
Okay, so that is about round robin. It's very clear, right? Very clear example here in the video. So you should know what is the problem with round robin schedulers now. Okay, you have enqueue, dequeue of the queue of processes lined up, and then what happened? It is shared, and then there is a time allocation. We call it quantum time. So how long it is allocated for each of the processes, and then what are the sort of problem faced if each processes was allocated longer time. Okay, if you, that is when you set into your program. So therefore you know that you should set a time that is not too long, not too short, okay, in order a smooth operation of the queue for round robin scheduling. Okay, are we okay with that?
Okay.
Yeah, it's very, to me, I feel it's very thorough. Okay, so this is a service counters problem. This is to show that waiting time is too long. So in this case, single queue, multi-counters, there are single queue, but there are many counters. People at the post office take a number and wait for their number to be called. Okay, so that is looking at the quantum time given for each processes. In this case, is the human waiting time. So if one person is given a lot of time to actually complete whatever transaction or whatever that he's doing at the post office, therefore waiting time will be longer, and that is no good for the person who's waiting, because that could lead to starvation. Starvation in the sense that, you know, they unable to, there is a static operation that cannot move forward until the operation is ended for that processes which are given priority to. Okay, also if it is too long, then you will lead to, you know, too long waiting, everybody is static, that will lead to some problem, we call it deadlock. Okay, that is going to be discussed in the next lecture next week. Okay, but that is what problems we relate with the real life examples, and also this round robin in queue. Okay, so this one again, using a queue to simulate a waiting line. For businesses, application in businesses, you want to analyze the time that each customer are allocated for the waiting for the service that they want to go for. Okay, that's why whenever you see at the counter, it says there that each customer is allocated about like 10 minutes probably. 10 minutes for the treatment, or in this case, for any business counter, what is the waiting time for each particular customer. And then if the time to wait for each particular transaction is too long, that will affect customer satisfaction. If it is even or balanced, that would be, that customer would be happy with it, you know, satisfied with the service. So that also lead to how many numbers a customer serve in a day. If you were to allocate how many seconds or how many minutes per customer, and that way, if you serve in a restaurant, for example, business premises like restaurant, if you have customers eating at your restaurant, the more it is, the more profit you get. Okay, so that also looking into how you get profit with more customers served. So that is all about allocating balance in your time for serving or giving service to each customer. Okay, this is application of queue in your real life. Okay, that's done, I think. Done. Not yet. Okay, another one is a computer. How many more? Wait a bit more. Okay, so we have computer simulation. Okay, so this is computer simulation of a real world situation to test various business scenarios. Same thing. For example, simulate waiting line with one serving agent. Okay, so this I mentioned already. You customer arrive at different intervals. Same goes to your processes. Somebody wants to print, for example, and then those who comes first will be served first, FIFO, first come first serve, and then those who come later on will have to line up way at the back. Okay, and then of course, if each of that particular processes or customer will be allocated similar time frame for the service given. Okay, to complete any transaction that they are coming for in a business premise. Okay, so this one is problem computing profit in sale of shares. So it says here, people buy shares in a particular company over a period of time. So last year, for example, one person bought 20 shares of Presto Pizza at 45 ringgit per share. Then last month, that same customer bought 20 additional shares at 75 per share. And today, that same customer sold 30 shares at 65 ringgit per share. So what is the profit? And which of your 40 shares did you sell? When computing profit for the sale of shares, so basically you will need to assume that you're selling in order in which you purchase them, which is FIFO. So how you're going to solve this problem is to design a way to record your investment transaction chronologically and to compute the profit of any sale of shares. So this is the application of Q in your program. Okay, so this is the illustration of Q of shares of stock. A indicates individual shares of stock. Individual means you alone. So you have priority given to your transaction based on the time frame allocation for each transaction. All right, so B is referring to group of shares. There are someone who's buying 30 shares, someone buying for 45, so then everybody line up in a queue. So each processes are allocated quantum time for waiting for it to be executed and served. All right, so that is queue of shares of stock. So there is a sample code computing profit in sales of shares here. Chapter 1, share purchase the Java, share portfolio the Java. Okay, these are actually an example of how this profit of sales of shares computed in or illustrated inside the code. As usual, I don't have this code. I will search into my other file, and if I have, I will share it during practical time. But I'm sure there is a code that I have to share with you for your next tutorial, next practical question. Okay, so this one I will check. Exercise. After you have gone through all the lecture notes, this is basically to just refresh you. For each application below, identify if a stack or a queue would be the appropriate data structure. Provide justification for your choices. Okay. Great. Okay. Something blocking here. A is your page visited history. How do thing? Okay. Page visited history in a web browser, access to shared resources, undo sequence in a text editor. Okay, so these are the situation of application for if it is a stack or a queue. So and then you have to justify your answers why you think it is a stack operation or stack application, or it is a queue application. You get what I mean? It says here, for each of the application below A, B, C, identify a stack or a queue would be the appropriate data structure. provide justification. So you have been given the examples of how you apply stacks and how you apply queue in our real world context. So these are given to you ABC. You're supposed to identify if A, B, or C is suitable for stack application or a queue application. So you have to go back and see through the examples. Yeah, page visited history in a web browser. What is it? Is it a stack? Is it a queue? Access to shared resources. Shared, usually we look into queue. Okay, so whichever stack or queue is applicable to this, you have to explain your choices. Undo sequence in a text editor. So if you recall, we have come up with examples of each application stack, the undo process. So which does this belong to, or which does this suitable to be applied? Which particular data types, stack or queue? Okay, so that is exercise 1.2. All right, so learning outcome for this chapter. At the end of this, now that we are at the end, you should be able to explain the benefits of abstraction. What is abstraction? Apply the use of list, stack, and queue. ADTs, abstract data types, appropriately to solve problem. Okay? So list, stack, and queue, those are your ADTs. Yeah. So you can go back and read through again. This one, I think the answers in the notes, A, B, C, search through, and then justify. This is an opinion base, okay, based on your understanding, right? So I think I have seen the examples which are given in the notes. You just have to browse through and give your answer here. But see, for example, undo sequence. What do you think would be appropriate for this application of which ADTs? Which one? Undo? Yeah, stack, right? Page visited, and then this one, access to shared resources. Shared meaning it could be the one which we mentioned earlier. You will have to look into the concept of list, stack, or queue. So access to shared, yes, queue. And then page visited history in a web browser. Which one? Page.
Stack.
Yes, correct. So that concept is basically how you would see the operation of stack, queue, and list, which is able to perform, right? So you know which one is which. Okay, so next one is your references. Hang on, this one. Okay, so there you go. You know how to explain. You understand a little bit of the application of the ADTs. And next is our references. So this is your main text. Okay, main reference, and then additional references. Intro to Java programming and data structures, and then data structures using Java for the addition. Okay, so these are the books, but there are a lot of other resources online, many resources. So I'm sure you know, and you have done everything, your references, right? Okay, so what do you think? So far you can understand concepts?
Yeah.
So far I can, but you know, there are some other things that you need to probably look into, right? Like this one, for example, you have been exposed to during your OOP, right? So that is a OOP characteristics, right? Information hiding, encapsulation, modularity. Okay, abstraction. What is it? So you need to know what is the term. What are the terms? Yeah, you need to know what are the terms. Abstraction, encapsulation, data hiding, and then abstraction, modularity. Because sometimes during the exam or test, there will be a question on asking you about what is it. Okay, what is the difference between information hiding, encapsulation? Okay, what is that? What is the difference in encapsulation and abstraction? Okay, so if you can see, I have added my notes over here. If you want it, I will send it to your email. Yeah. Okay, because I posted there in the GC as well, but those are what is given. Yeah. Okay, so I put on extra information so you can get yourself understand the concept better. Okay, so any problems?
No.
No? Did you check your question? Did you check your, what do you call that? Your practical question? We are moving towards number 3, stacks. Stacks, yeah? The week 2, we are moving towards stacks. I think stacks and queues, if I'm not mistaken, there is a question in that, yeah? Stack and queue. So, but later on, we will see into that, okay? And I will show you some codes as well that you can accommodate with your questions as usual. And then, okay, if there is no other question, we will conclude our lecture and we will meet again later on at 2 p.m. for our lab session, practical, right? Yeah. So Kevin, don't forget, please submit that into the submission box, yeah?
Miss,
Yeah.
is there any assignment?
Assignment, I actually have a lot of the documents. I will post it later on. Those are actually not the question yet, but those are the documents that you need to go through if you have queries, like for example, what do you need to do for the assignment? What are kind of things that you need to, how do you present your assignment questions, answers, and then your rubrics, and then other instructions. But I don't see that there is a question there yet, but maybe question is coming up soon, right? Should be this week. Yeah, but what I have, I will post in GC. Okay, I will post a material in GC.
Okay.
Yeah. Okay, so don't worry about it. I'll post all the material that is required first. You have a look at it, and then if there is a question for, I think I need to check. That is for me. I think it's just all the documents that is needed, not the question. Yeah, don't worry about it. We will discuss about the papers, the discussion during your practical if we have time, little bit, and then you can proceed with your question practical for stacks and queues. Okay, class?
Okay.
All right. So with that, no further questions from Noel or Kelvin?
No.
No? So if there is no questions, we will conclude now so that you get time to analyze questions if you need to, and then we bring forward to our practical class later on. Okay?
Okay.
All right. So I see you later at 2 p.m. Thank you for your
Okay.
attendance. Yeah.
Okay. Thank you, Miss.
Bye.
Okay.